All right, in this video, I'm going to cover the 2009 free response questions number 1 through 3. All right, for question 1A, you needed to create a graphical display that represents an association between gender and job experience. So you have two quantitative variables, and you're looking at doing a graphical display based on the contingency table. So you're talking about a pie chart, a bar graph, a segmented bar graph, which is what I ended up doing, which I'll go through with you here. So for the people who never had a job, I just did the male out of the total and the female out of the total to get the 40 and 60%. Summer only, male out of the total, female out of the total to get 54 and 46%. And part-time throughout the year, male 12 out of 20, 60%, and female 8 out of 20, 40%. So when you're doing your graph here, you need to make sure you label both axes. So on the vertical axis, I have percent. Because I did a segmented bar graph, it needs to sum up to 100%, which you see here. And then I have my three categories, the way I set mine up. Never had a job, summer only, and they had a part-time job the whole year. And then I'm just taking my percentages. The 21 out of 52 for the male is 40%, plus 60% gets me up to 100. Same thing for summer only, and same thing for part-time. Now, taking a look at the rubric, what we needed to do to earn credit was this. All right, it's essentially correct if an appropriate graph is drawn correctly and all labels are provided. So you notice how important labels are right away. It says a segmented bar graph, a bar graph conditioning on gender, and pie charts are acceptable. So you'll notice I did that. If your graph is drawn correctly but some labels are missing, that's going to be partially correct. So based on what I have here, I have the labels, I have an appropriate graph. That's going to earn me essentially correct. For part B, what they're asking us to do in part B is summarize what the distribution shows. So we have, looking at the rubric, it's essentially correct if you correctly discuss percentages for both genders within each job category of job experience. So you'll notice what they did. The females in the sample were more likely to have never had a part-time job than were males. Females were less likely than males to have had a part-time job during the summer only or just for the whole year. And if there's no association, then they would be about the same. Okay, so let's see what I wrote down here. So there is an association between gender and job experience. Females are more likely to have never had a part-time job. Males are more likely to have had both a summer job only and a year-round part-time job. Overall, males are more likely to have had a job of any kind. So going back to the rubric. So I didn't explicitly discuss percentages, but neither did they in their model solution for both genders within each job category or within each category of job experience. So I did that because I'm talking about the three categories here. Females are more likely to have never had a part-time job than males. So that takes care of that category. And I'm talking about summer only and year-round. So I've compared those and I've talked about all three. So that would be essentially correct. You'll notice on the solution here, if you're only doing it within one or two of the groups, you're going to get a partially correct. Okay, going to part C, they want to know what kind of test you're going to want to do and write out the null and alternative. So it's essentially correct if you recommend using a chi-square test of association, or we call the test of independence, and then you put your null and alternative in context. Partially correct if you recommend using an incorrect test, but you have the correct hypotheses for a chi-square test of association or independence, or gives the correct name of the test, but does not give the correct hypotheses. So you'll notice here, I did a chi-square test of independence with degrees of freedom equal to 2. That's extraneous. I didn't need that. Should be used. The nulls, gender and job experience, are independent. You could have also said gender and job experience are not associated. The alternative, gender and job experience are not independent, or gender and job experience are associated. Okay, I have the correct null, I have the correct alternative, I have the correct name of the test. That's essentially correct. I have three responses. All three were essentially correct. That's going to earn me a 4 on this question, which is 7.5 points. Okay, let's look at question number 2. Okay, in question number 2, For part A, everything's graded as an EP or I. It's essentially correct if you clearly indicate which distribution is being used, along with your parameters, your mean and your standard deviation, and you calculate the correct percentile value. Okay, so there's really three components they're looking for: the distribution, approximately normal, the parameters, the mean and standard deviation, and then the actual calculation. And you'll notice, like we did in class, this suffices as distribution and parameters. Okay, so there's my distribution. It's approximately normal. Mean, standard deviation, how do I know it? They said it's approximately normally distributed. Okay, so when you're given a percent, you use inverse norm. So there's 70% below. That gives me a z-score of 0.5244. Z-score equals stat, which I don't know, minus the mean of 125 over the standard deviation. And just solve that out, 128.41 feet. So that's the correct value. You'll notice they rounded to the nearest tenth, whatever. So I have the distribution, I have the parameters, I have the correct value. That's essentially correct. In part B, it's essentially correct if you recognize the probability as an application of the binomial distribution, find the probability first, and then the probability of success, and then using this P to find the correct binomial probability. There's three components: the distribution, the parameters, and the calculation. And I already know that I messed this one up, but I wanted to leave it on here because that's what happened. Okay, so I'm trying to figure out, this is where I didn't read carefully. What's the probability at least 2 out of the 5 cars will stop in a distance that is greater than the distance calculated in part A? So we know 70, that was the 70th percentile. So what you'll notice that I screwed up here is the probability of success is 30%. If 70% stopped in that distance or less, then 30% stopped in that distance or more. As far as the actual calculation, check in Bernoulli trials, there's 3 things I want to check. There's 2 outcomes: they stopped in time or they didn't. That is met. The probability that they stopped in time is consistent, and each trial is independent. One car stopping in time should have no influence on the next. So this does represent Bernoulli trials. So I can define a random variable as the number of cars stopped in greater than 128.41 feet out of 5. Don't forget your sample size. So X is binomial. There's my mean. There's my sample size, N, or my number of trials, and the probability of success. That 0.7 is incorrect. That should be a 0.3. And then I did this consistently correct. 5, choose 2. These should be switched, the 0.7 and 0.3. So that I'm going to notice is not correct. But whatever you're starting at here, if it's not 0 and you're going at least, this needs to be 1 less than that as far as plugging it in your calculator. And anytime you're not starting at 0, you're doing 1 minus binomial CDF. So you'll notice here on their solution, they, instead of summing up the formulas 2 through 5, they just did 1 minus and got rid of the formulas for 0 and 1. That's not really the way that I modeled it in class. You can do that. You're going to earn essentially correct. You're probably more likely to do a formula for 2 through 5 and get that 0.4718. So going back to the grading here, I have the correct distribution. I have the binomial distribution. My parameters are incorrect, but my calculation is correct based off my wrong parameters. So I have 2 of these 3 components met. So you'll notice for partially correct, 2 out of the 3 components have been met. So grading this would be a partially correct. Okay, for part C, they want to know what's the probability that a random sample of 5 cars will have a mean stopping distance of at least 130 feet. Okay, so this is kind of a unique situation, and I'm going to explain that's really important right now. You're going to need to use the normal model even though you have quantitative data. And the reason is this. This standard deviation is not from a sample. It's from the population. So this 6.5 represents sigma. We always use the t-distribution if we don't know sigma. That extra variation is what causes us to use the t-distribution. Because we know sigma here, even though I have a random sample of 5 cars, I'm using the normal model. So you're going to see me calculating a z-score here. Okay, there's a couple components that you need to meet. Sampling distribution, parameters, and calculation. Okay? So the key is the sampling distribution is going to be approximately normal with the appropriate mean and standard deviation. So as I calculated this, all right, so as I calculated this, the mean is going to be 125 still. Your standard deviation or your standard error is going to be sigma over the square root of n. That being on your formula sheet, sigma over the square root of n, okay, because I know the standard deviation sigma. So it's 6.5 over the square root of 5. So there is me getting the correct sampling distribution with the parameters. 2 of the 3 components, I'm doing the calculation to get the probability. Let's double check with what they have. Z-score is the same, probability is the same. We're good. So I have all 3 of those components met. That's an E for grading that. Okay, as far as scoring this out of 4 points now, I have 2 E's and a P. So 2 parts essentially correct, 1 part partially correct. That's going to correspond to a 3. So this is going to be a 3. All right, next up, question number 3, which is going to be dealing with sampling and experimental design. This is a really interesting question. It seems pretty straightforward, but it can be pretty difficult to earn credit on. Okay, in part A, there's a couple of key things here. We're analyzing the change in test scores post-test minus pre-test, so it's the same students. So this is really a matched pairs design that we have going on. We're describing a method for assigning the 24 students to 2 groups of equal size. That's important. That allows for a statistically valid comparison between the 2 groups. Okay, so as I'm going through this here, essentially correct if a proper method of randomization is described that creates 2 groups of equal size and assigns the named treatments to the groups in a manner that a knowledgeable statistics user would employ to the 2 groups. Okay, so you have to, 1, create equal size groups, which shouldn't be a problem, and 2, make sure you're very clear as far as what group is going to what treatment. Okay, so I said list the students in alphabetical order, then number the students using this list from 0, 1 to 24. Use a random number generator to select the first 12 numbers. This is key. You need to ignore repeats and numbers 00 and 25 to 99. These students will physically dissect frogs, and the remaining 12 students will do a simulation dissecting a frog. So I have 2 equal sized groups using randomization, and I'm talking about the named treatments. The first 12 are physically dissecting, and the remaining 12 are dissecting it using the simulation. So that's going to earn me essentially correct. Okay. Just a couple notes here. In using a random number table, if numbers are specified, the students must work with 2-digit numbers. Okay. So if you're talking about a random number table, that's what I would encourage you to use a random number generator. Don't say table. It'll give you a little bit more leeway. Okay, for part B, this is where it gets a little bit interesting. You got to kind of dig deep here. You want to know how this method of self-selection could jeopardize the valid comparison between the 2. And you have to provide a specific example. So give an example and then kind of tie it into why it's going to create a problem. So grading part B, it's essentially correct if the example gives a reasonable characteristic of the self-selected students in the study, and you explain how it could be associated with changes in the differences between pre and post-test scores. That's the key thing that so many students forget, is tying it into the response variable, what we're trying to measure, figuring out how that's going to be a problem. Okay, so my solution looks like this. I said maybe all students who did really well on the pre-test decide to simulate the dissection, and as a result their post-test scores are very similar to their pre-test scores, and as a result the simulation does not show an improvement in test scores, and it may be deemed an ineffective model to use to help students. Okay, so my example is all the kids that did well on the pre-test decide to use the simulation method, And now how am I tying it into the changes and the differences? Well, I'm saying there's going to be a very similar score between the pre and post test, so it's going to look like this model was ineffective. So you'll notice in their solution, okay, they say something very similar. That they would all choose to, let's see, they already know a lot about frog anatomy, so they'd expect those students to be less likely to show a change between the pre and the post-test scores. Okay, so we went down a very similar route here. Okay, the key thing is the other group is going to see a larger change and than those who didn't do the actual dissection. Okay, so the frog dissection group might see a larger change in scores because students entering this group are those with the lower pretest scores and who are more likely to show great improvement. Okay, so two components you're trying to meet: a reasonable characteristic of self-selection, and then how it changed the differences between the pre and the post-test. If you're doing one of these two things, if you give an example of a characteristic and a weak explanation, which is what most people did when they took this exam, you're going to get a P. All right, so this is going to earn me an E. I've done both of those two components. Grading, there's only two parts, so E's are worth 2 points, P's are worth 1. So both parts essentially correct here is going to earn a 4. Remember, your goal is 2 or higher on question 1 through 5. Okay, that's it for this video. Next video, I'll take a look at question 4 through 6.